In a recent video, I showed a little module that I'd made which takes a micro USB connector and you can plug in a string of lights. I've actually got a cob at the moment, but it's designed to take a parallel string of lights like these. And it was originally designed to take a passive infrared module. And the idea was that whenever you walked into the room, it would power the lights up, and it just meant that you always had a string of lights lit, but it would draw so little power when you weren't in the room because they would automatically cut off that the unit would last a long time on a charge. Noting that you can only use the USB power supplies that put out 5 volts continually. The bigger ones, the intelligent ones with the little indicator LEDs and the button on them, they'll just go to sleep after a while if they don't detect the load, and then you have to reset it, which is kind of pointless in this application. However, after I'd made that, I decided to make a few more, and I ordered up some passive infrared modules, but I also thought, let's take a look at these little microwave modules because they're so readily available now, and I was quite interested to see what their current consumption is. Because the necessity of this circuit here is it has to be fairly low standby current, and with the standard passive infrared modules, particularly ones based on the BISS0001 chip, which is really common, their current consumption is measured in microamps. And I pondered, are these going to be able to draw low enough current, even though they've got an RF oscillator running all the time, to actually, pose such a low demand on the power that the battery, the charger, will last a long time in standby? So I ordered some, and when I got one through, these incidentally, they're called RCWL0516 modules, and you get 10 online for about $6.85 American dollars. That's buttons. That makes them less than 70 American cents each, including shipping, which is just ridiculous. And I got the first one and I connected it to I made a little loom up for it. I'm just going to make sure I plug this in the right way. Let's do this test, in fact, and I'll show you how much current it does actually draw. I'm just double checking my settings here. Let's bring in a power supply. Let's connect negative to here. And this little test lead I've got powers it up. It's also got a LED with a resistor in series just to glow at very low intensity, just to show it is actually working. I'm going to bring in my scandalously tacky little cheapy meter here. The reason for that is simply because these little meters you don't have to change the leads about. They make ideal little bench meters when you're testing current. So I'm going to connect that there, black onto the red, because it's actually going in series. And if I activate the bench power supply now, 5 volts, it's showing a current of 2.6. It's gone up to 3, but in the standby mode, it's about 2.6 milliamps. That's not bad. It's not as good as the passive infrared modules, but it's really not bad. It's a lot less than I was expecting. But while I was doing this, I thought, okay, let's reverse engineer the circuit and see if we can, because I have to say that the microwave detectors are rocket science. I will openly admit that the way they operate is pretty clever and takes people with a knowledge of RF electronics to fully understand it, but let's give it a go. So I shall put this module back in here. I've got this cob LED just for brightness, just so you can see the reaction. At the moment, when I disturb it, it detects movement in the vicinity, once it's stabilized, it runs for approximately about 3 seconds before it cuts off again, but you can adjust that time delay. And if you keep moving about in front of it, it keeps re-triggering, it extends the time delay. So as long as there's movement in the room, it should keep the lights on, but you can extend the delay to fine-tune it if you wish, and I shall show you how. So I do have zoomed images of these so we can examine them, because I've already done a bit of exploratory work and I've done some schematics and things like that. So to start off with, I'm going to show you a slightly illegal circuit. A circuit I used to build when I was a kid quite a lot, because I was into RF transmitters for a while. Let's nudge the intensity just a tiny bit. Yeah, let's do it like that. And zoom up a bit. And focus down onto that. So in the past, you could build a very simple microtransmitter using a Colpitts oscillator. And you had, say, it was a 9-volt battery plus 9 volts. You would have a simple tuned circuit which would have a capacitor and an inductor. And the inductor was so small that you literally wound the inductor around a drill bit, just maybe 5 or 6 turns, And just to tune the oscillator, you could, on the fancy ones, you had a variable capacitor, but on the simpler ones, you just squished the inductor to actually tune it slightly by changing its inductance. But that went to a fairly common transistor, was the 2N2222, or the ZTX300 was also one. And that would then go down to a resistor, say around about, I think it was about 470 ohms I used to build them with. And that's the 0 volt supply. 0 volts the supply. There'd also be a little capacitor across here. Typical values, 8.2 picofarad, really low values, because it had to transmit, these had to transmit in the FM range of about 300 megahertz. And then the bias for the transistor was either just a single resistor going to the base of the transistor, or sometimes two, as is the case of the microwave oscillator. And the circuitry went further. You had the audio signal going in, would actually be coupled to that with a capacitor, and it would modulate the frequency that transmitted at. And then you'd have either an antenna coming straight off like that, or a little capacitor there to make it more stable. It was a very, very simple circuit, but it worked really well. And you could, when you made these bugs, if you fine-tuned the design, they transmitted for a long distance, even though they were running at low power. Illegally running at low power, yes. Still transmitting without authorization, but you know what? It's just one of those things. So looking at this circuitry here, I'll show you the pictures that I printed out. It turns out that these microwave movement detectors actually work in a very similar way, but they are operating in the sort of gigahertz instead of megahertz. And the circuitry, let's brighten this up a wee tad. The circuitry gets a wee bit weird and specialist here. So what we've got here for a start is the RCWL. I guess this is this a manufacturer that's had this chip custom done? Because this is a BISS 0001, but it's got one custom modification to it that makes it completely different. And it's to do with this pin down here that has a completely different function. But we'll go into that shortly, because let's take a look at the circuitry itself. We've got the antenna here. And that is basically, the antenna is also the inductor. We're talking microwave frequencies where just a little track, a wiggly track like that, can have a huge, profound effect. And I have kind of reverse engineered this. So let's go over it. So all the plated through holes around the outside, they're there for a reason. They are basically a ground plane. It's lots and lots of screening. And this track coming in here is positive. It's 3.3 volts. More about 3.3 volts later, because it's interesting how they derived it. This is a microwave transistor. I'm just going to turn this over. In fact, it's easier for me to read it, the layout of the schematic, if I put it over this way. So here's what we have. We have the 3.3 volt supply coming in, and the first thing it hits is these three capacitors, which appear to be 100 nanofarad decoupling capacitors. After I'd reverse engineered this, I went online. I was looking to see if other people had done it. Yes, they have. And they'd actually taken the capacitors off, I'm guessing, and measured them. I didn't do that. I tried measuring them in situ, had no luck, so these are other people's measurements, but they are quite feasible measurements. So we've got the three 100 nanofarad decoupling capacitors. That's tied to the negative rail. That's tied to the negative rail. That's tied across there to the negative rail. And then they're all common down to this track here, which does something very interesting. It doesn't just go down to the transistor. It actually forms a screen round the other side. It's very, very weird. It will make sense to people who work with RF technology. I've often said that, you're never going to be an expert in every single area of electronics, because there are so many specialist sectors, and there are people who their whole life is spent working with microwave transmitters and technology, and it's such a completely independent area of electronics. It's a really niche section, and that's what this fits into. Someone obviously spent a lot of time designing this. It really is quite special. So there's the three decoupling capacitors, which makes sense. They need a really stable supply for oscillator stability. Then, with this 100 ohm resistor here, from the positive, they couple that through this capacitor here, which is another 100 nanocapacitor, and it provides a stable supply. It provides a stable sort of base supply for the transistor. Then they use these two resistors here, one connected to negative, that's the 2.2K, and the 4.7K, 472, that's 472 zeros, 22 and 2 zeros, so that's 2,200, that's 4,700. They then feed to the base of the transistor, so that's the base. And this is the collector, and unusually the inductor is on the emitter. So that's collector, emitter, and base. So that biases the transistor into a sort of semi-on state. It makes it sensitive to any disturbance on the base or the other connections relative to the base. Then they have the inductor, and I've just drawn it as it is. You could draw it as a single loop inductor. I haven't a clue. Seriously, it is in the region of microwave electronics. There's capacitors as well. This track coming down here is part of a capacitor as far as I can see. And that is all down to this on the back, which is connected to the base. This plate, I think it's a screening disc, but it may also be acting as a capacitor, coupling horizontally out to this outer ring, which is connected to positive. It's very hard to say. It may have the positive there may be actually a screen around the transistor. This may all be screening and protection against external interference, or I really, seriously, it's not in my field of electronics. Other than that, it looks as though it is coming down to being the Colpitts type oscillator, but with capacitors that are built onto the circuit board. I'll try and draw them in later, but it's complex. The resistor down here is the equivalent to what I used as a 470 ohm resistor. It is, let's see, this is going across like this. So this comes down, there's this 221, which is 22 and 10, so that's 220 ohms to the 0 volt rail. Plus there are also two 33 picofarad capacitors, this one going to the 0 volt rail and this one going to the 0 volt rail. I don't know if the positioning is important here, it's just how it is. I know that in the world of microwave technology, curved edges are really quite important. You can't have square edges. Everything's curved except this bit. This is not curved, this is square. The signal then, having had some sort of element of filtering, I'm guessing, I guess that's what that is, then goes through this 1K resistor and gets filtered by what is apparently a 1 nano. And that then goes via the track on the back of the circuit board. Let's find that track. That's this track here. It then goes up to the sense input of the chip. Now, to try and work out what was happening, with those things in the back, those antennas, I made a translucent transparency. And if I lay it over and line up those holes, you can see that the circle completely covers the transistor, and technically speaking, it's tied into the base. The largest areas that are covered are here and here. Could those be capacitors coupling to the base? The outer positive also comes round and it eclipses over that pad. Is that deliberate? Is that, I'm guessing that must be extending down, so that then gives a certain capacitance to the positive connection to the base. So let's draw that in the circuit diagram. There's an element capacitance to there. That's this bit here. It's very low value. And technically speaking, between the base and the collector and the base and the emitter, there are also capacitors. I thought maybe the circle around the outside was going to interact in some way with the antenna here, but it eclipses it here. It eclipses it here. and it eclipses it here, but I don't know if that's a deliberate thing. I don't know if that has a particular effect. Is it essential in microwave transmitters to have multiple tap points? Let me just bring this into the center. Is it essential to have multiple sort of capacitive tap points, almost like along the antenna? Like, say, for instance, if that's the positive up there, it's almost like it's got capacitors tapped along it. It might just be coincidence. It might just be the fact that they need that outer positive track to screen from external interference. But here's what happens, as far as I can see, to actually do the sensing. This is transmitting microwave energy. The amount of energy it's transmitting, if we consider that we've got a 3.3 volt supply, 2.6 milliamps, it's not going to be 100% efficient at all. But that would equate to about 10 milliwatts. I would say the efficiency is such that you're only going to get 1 milliwatt of RF energy transmitted. It's just going to be a very low level signal. And when you have a signal sort of coming out from a radar device, it experiences Doppler effect. And if you move towards it or away from it, it disturbs that. It sends reflections. And if the reflections are static, if it's just bouncing off things in the room and it's picking up reflections, the voltage here will be a very controlled level. It'll be very, very stable. And when something's moving in the room though, it effectively changes the load on that oscillator. It's trying to oscillate at the frequency it wants to oscillate at, which will be determined by the capacitive and inductive elements here. It's not precise, it's not crystal controlled or anything like that. It is just running at a frequency. And it's by default, it wants to oscillate at that frequency. If it detects disturbances coming in that make it harder for it to oscillate or easier for it to oscillate, then the voltage there will undulate up and down. And that then gets coupled through this resistor. It's get filtered by this capacitor here, and then it goes to the sense input of the circuitry that detects it, the BISS circuitry. Now let's take a look at... Oh, one thing I should mention. If you notice this is white stuff all around it, that's just a bit of white tack, because I actually stuck this down. I had to stick it down really level to get the circuit board, the picture of the back. Oh, talking of which, the picture of the back, you've got 3 pairs of pads, R, CDS, R, GN, and CTM. I'll tell you what they are afterwards, because they're quite interesting. They allow fine tuning of it to suit your requirements. Let's get the notepad out of the way. So the circuitry is effectively, it's like a BISS 0001, which is a passive infrared detector. The normal expensive passive infrared component, that's this bit, actually has a window that allows light to shine on 2 sensor modules that are wired in series, but they're wired in inverse series. And they feed to a little MOSFET, and the MOSFET has a slight resistance to give stability. And then what happens here is that they detect body heat, and they result in a slight... I'm just going to tame this down a bit. They detect body heat, and they generate a very slight voltage, and that the FET in here will undulate up and down. Now, the reason they've got 2 in inverse series is so that if there's an ambient level coming in through this window, it will kind of cancel each other out. Each will be generating roughly the same voltage, and you'll get a fairly sort of... It cancels out the rest of the room, so to speak. In front of these, they normally have a series of lenses. If you've looked at let's take a look at this one. It's got the little sort of patterned polythene lens in it. Polythene because it passes the long wave infrared, and it focuses into lots of dots as you walk past. So instead of just being an ambient level when you walk past, you'll get an effect where it will focus your body heat onto first one sensor, and then the other. It will actually pass from backwards and forwards between them, and that results in the output suddenly going up and then down from the sort of average level. So that's how the passive infrared sensor works. And what happens when it goes into this chip is it amplifies that, and then it filters it, and it looks for a significant transition. So it makes it perfect for use with these infrared modules. And effectively, the output of that circuit is it's replacing all this, and it's going into that input. And if you look at the input of these, the inside, the circuitry, what's inside the chip, basically, the block diagram, it goes through, it's got an op-amp which does the first level of amplification and filtering, and then it goes to a second op-amp that does a second level to boost it even further. And then it goes to comparators, and there's a string of there's a resistive divider here that sets specific voltages, and as soon as it clips over those voltages, it actually triggers different functions that then signal to the main control chip. And the control chip runs, it's based on a little timer. It's got a RC oscillator that you can change the components of to actually deal with the timing. And it also determines via this input A whether it can be re-triggered. Interestingly, they've repurposed a chip. They've repurposed this pin here. Pin 8. Pin 8 used to be, well, what is pin 8 listed at here? It's listed as the voltage reference pin. It's not the supply pin. The supply pin, I believe, is pin 11. 11 is yet the drain pin, so pin 11 is the supply. What they've done is that this one, they've actually put a voltage regulator inside it. I'll show that another thing here. So instead of this actually acting as a reference and being tied positive, they've taken that into a little low dropout regulator, and it puts out 3.3 volts, which means this chip can theoretically operate from 4 volts up to about 28 volts, they say, and what data sheets you can find. It's a very, very vague chip. It seems like this company has just optimized and put their own name in it, so to speak. So what it means is that it now puts that 3 volts out on the VDD pin. It sort of self-powers from that input with a variable voltage range. Keep in mind, this isn't the BISS 0001. This one is the modified one that's got this voltage regulator inside it. The pads on the back. Let's get the picture here. So the circuitry used in this is pretty much, the chip is almost, apart from that voltage regulator, it's almost a complete clone, and the component values are very, very similar. So they have, the oscillator is based around this resistor here and this capacitor here, but they've also got a set of pads, C, TM, capacitor, timing, that if you stick a capacitor across it, you can actually slow that oscillator down. That extends the time. So say, for instance, at the moment when this is powered up, it runs for, let it stabilize. It runs for about 3 seconds before it re-triggers again. It's just at the moment that's all the circuitry is just stabilizing, so it won't be so sensitive initially. Once it's stabilized, I'm just going to make sure I get the right bit here. Once it's stabilized, it triggers for about 3 seconds and then cuts off. And if you move again in the vicinity, it will trigger for 3 seconds and cut off. I tacked, the original capacitor in there is 10 nano. I tacked a 100 nano across the back, so theoretically that's about 11 times the capacitance. And rather accurately, when I put this in, shall we time this? Let's let it stabilize, and yeah, it's going to take a while. It's going to be quite some time. I'll let you time it while I describe the circuitry. This is going to be awkward because any movement is going to re-trigger this, and me trying to count for 30 seconds. Suffice to say, it now runs for about 33 seconds before it resets. So you can choose the value of the capacitor and put it across those two contacts. It's the ones that are here, CTM, capacitor timing. Other components, you've got RGN. That's the resistor gain. Not enough room to draw it in here, but it's the first stage of that op-amp that amplifies the signal, and it's what's called the negative feedback. And by adding it, by default, it's got a resistor value of 1 or 2 megohm. You can tack another resistor across that to actually reduce its sensitivity, and what that's going to do is it's going to reduce the range of the unit. It means that whereas by default this has a ridiculous range of about 7 meters, it will actually reduce that. You can probably reduce it just a couple of meters, just to actually, if you don't want it to be too sensitive. The other resistor position is called RCDS, and that's for the cadmium sulfide photocell. Now, you can put a cadmium sulfide photocell on this circuit board, CDS. I'm not so sure I'd put it right up close to the microwave circuitry like this. But you do have the option, it's taken over to here as well. You can put it between the CDS and the ground if you want an external LDR, light dependent resistor, CDS cadmium sulfide sensor. But what this does is, by default, the circuitry has a value of resistor built on already for a typical value. But you can make it, you can change the sensitivity so it comes on sooner at night if you want. You can make it less sensitive to light by adding another resistor across here and tuning that value so that it just balances off with the LDR you've chosen, the light sensor. And that's what the RCDS is for. It just lets you tune that. So it's very interesting. The circuitry is basically a little simple RF oscillator that is detecting the movement of the room by that interference from the Doppler effect, the waves being bounced back, and if they're slight out of phase, it makes it a wee bit harder for it to oscillate, so it draws a bit more current, and with the movement of the room, it just detects that undulation up and down. Then it gets detected by what is basically a standard body heat detector chip, but without the expensive component, the body heat detector. In this instance, all it's got literally is, these capacitors would all be needed for the body heat detector chip as well, the thermoelectric detector. Is that right? Pyroelectric detector? That's better. But they've replaced it with this little transistor. The transistor, incidentally, is a BFR 520. It's a standard. It goes up to 9 gigahertz. Or if you like Back to the Future, 9 gigahertz. Very, very interesting little circuit. Now, have I covered just about everything here? Oh, that says 32W. W is the country of manufacture. The 32 indicates that this is the BFR 520. The W indicates that it was made in China, because it could be made in Taiwan, Japan, or China. In this case, the W indicates China, which kind of fits in with the whole fact that this is a cheapy Chinese module. But they're impressive. It's also worth mentioning that this is screening. The back of the circuit board is less sensitive to the front. This, within little snake antenna, is the side that's going to be the most sensitive. You're also supposed to keep it away from other metal surfaces, because the metal can actually act as capacitance, and I suppose it'll affect the inductance of that. So you don't want to have anything within about a centimetre, I guess, of the metal of the back, and you definitely don't want metal in the front, because that would screen it, it would stop it sensing. I wondered if the current would go up and down, so I got a blade and I set it up. I put the unit on the bench, I parked the blade in front of it, moved it closer and closer. It did affect the sensitivity, it didn't affect the current. If anything, when the blade was up really close, the current went down slightly. And that is more or less it. It's currently set, the device pin number, which pin is that? Pin number 1 lets you choose. If it's tied positive, and you don't really have much choice here, it is by default, it's actually part of the positive path to the oscillator. It's tied positive, which means it re-triggers. So if I'm moving about continually, that'll keep re-triggering it and this light won't go off. If you had that, if you lifted that pad and tied it to negative instead, that would then put it into a mode where it triggers, but then it actually will always turn off before re-triggering again. But to be honest, this mode, the one that comes with, is the best type of mode to operate it with. And that is more or less it. Very, very interesting. Those of you who are into microwave technology will be more familiar with what's happening in this circuitry than I am. But I can work out from this, it is using inductance on the circuit board, it's using capacitance on the circuit board. Those are the two things that are deciding the frequency of that chip. I wonder if changing the outer diameter of that, I don't think so, actually lets them fine tune the frequency. Don't know. It's very complex. Very neat though. And I'm not going to wait for 30 seconds for this to reset. Just take my word for it that it does, after there's no movement being detected in this room for over 30 seconds, this light will go off. So very neat. well worth getting some of these. I'll put a search link down in the description below. And yeah, they're cheap as chips, and they work very well. And because they are low quiescent current, they're perfect to use with that circuit, the little module there, because it's not going to impose too much a drain on the battery. And if anything, it's going to make it more sensitive so that it will detect you entering the room. You don't actually have to cross the path of the infrared sensor to trigger it. So very, very neat indeed.